So, hello everyone. My name is Grebennikov Roman. I'm from Russia, and I work at a company called Findify, and we do search and recommendations. And this talk is mostly about the problem we encountered doing this in a large scale. That's my Twitter, email, and my face. You can send me some messages after the talk. For the product recommendations, the problem itself can look like trivial, but it becomes not so trivial when you have thousands of different merchants using it. It should be updated online depending on different conditions. It should be personalized per user while he's browsing the website. And to do this and to quickly update your machine learning models, you need to store a lot of different user behavioral data in your memory. And that works fine when you have 1,000 users. It's acceptable. But when you're going more and more users to keep in your memory, it can be not so easy. That's what we got a couple of months ago. And if you're going to store a lot of user behavioral data in memory or just another data, you name it, you need to go to different directions, but the major one is just let's just have one huge heap per application, like 32 gigabytes. We don't care, it will fit everything. And when you start doing this, you are going to play a game with garbage collector. So you're either trading your throughput, application throughput, or latency, and it will be cool to don't play this game because you will lose anyway. And having 32 or 40 or 60 gigabytes per application is really costly because your financial department won't like it. So the journey starts usually when with the case classes. When you learn Scala, everything looks like a case class, and it's a good idea when you decide to model your domain with case classes. So let's imagine that we have this case class, like a page view with two fields. One of them is identifier of, I don't know, product and timestamp. And here comes a short quiz. So we have an instance of a page view. I guess you can see it somehow. So it's a page view with an identifier, which is string of 4 characters, and timestamp, which is long, which is approximately maybe 8 bytes. And how much heap does the page view use? That's an interesting question, but before voting, I will just try to mess everything up. So we know that the case class is actually a Java object, and Java objects have object header. So we know its header most probably will be like 12 bytes. The string itself can be, on Java 9, it will be maybe 4 bytes. On Java 8, it will be 8 bytes. The long is also 8 bytes. So if we sum it, we'll get, we'll get 24 bytes. So who's thinking that it can be 24 bytes? You can just raise your hand. So everyone feels that there is a trick. Yeah. Yes, but your task is to find this trick. But we forgot that the string itself is an object, so you need to have a reference to this object. And the string itself also has an object header, and so on. And maybe it's 64 or 68 bytes. Who's voting for 68? 48, sorry. Or no one? Oh, so the pessimists are here. So yes, but the string itself is not only an object, and it's not encapsulates bytes right there. It has a reference to an array of characters. So an array is also an object with a header, with a length, and you need to reference it. Maybe it is 72 bytes. Who's voting for this? Good. And we forgot about padding. Object padding. If your object doesn't fit into the 64 bytes boundary on 64-byte architectures, JVM will pad it with some free space to get not to strike with the performance problems when objects are unaligned. So maybe it's 96 bytes. Who's no pessimist? There is one pessimist here. But the major part of your was right. It's about 72 bytes. It's not exactly 72 because it depends on multiple things, but it's about 72 bytes. And let's just understand why it is happening. And for that, we will try to dissect our page view case class And for that, we will use a tool. Oh, sorry. We will use a tool called JOL, Java Object Layout. There is a JOL integration with SBT, so you can do like JOL internals page view, and it will dump you the internals, how the layout of this page view it looks in the real memory. Okay, so maybe it's not that readable, but the interesting point is laying here. So we have 12 bytes for object header. It can be different depending on the Java settings. The reference for our string is 4 bytes. We have long here, and the object is 24 bytes. But we know that we also have a string. So let's just see what's up with our string. It's Java lang string. And inside the string, there's a bit more data here. You might be scared about that, but that's not, I will explain it. So we still have 12 bytes for a header. We have a reference to the array of characters for the string, and we have a hash code right here. And we have some padding lost due to the next object alignment. On Java 9, it will be a bit different because of the compact strings, but still mostly the same. I don't know the way how can I dump the internals of the array object in with JOL, but you have to believe me that it is the problem is the same. It still have header, it still have has length, and so on. So if you draw it without all the scary letters, so it looks like this. So it's just header, there's time, the reference, header again, hash, some padding, again header, some length, and finally characters of our identifier. And if you sum all the things together, it's not the complete list because there is no padding, and I forgot to put the string hash here. But anyway, it will be about 72 bytes. And that's very disappointing when you start measuring, because if you are like traveling in the world of monads, you don't really think about this, but the reality strikes back, and you have to deal it when you have to optimize your application finally. So the case classes itself are rarely used without collections because it's a really convenient way to use them. And for example, it's a very simplified definition of a Scala collection list. It's just a case class of head and tail. So it's still a wrapper object with a header and 2 references. And the memory layout of all that stuff looks like this. So it's a lot of references to different things, a lot of headers, a lot of different objects laying here, and I forgot to draw the array of bytes down there, but that's a lot, and they are distributed almost randomly in RAM, and it's always a problem for your processor to fetch this memory from RAM when you're really concerned about performance. So let's have another case story. So we'll have 1 million of page views, like this, just a list for 1 million items with a page view, but we'll use another tool called Java Agent for Memory Measurements. It's just a Java agent which can plug to Java Instrumentation API, and you can feed a reference to an object, and it will traverse all the references from there and compute the memory usage, the real memory usage of your collection. And And if we go this way for our 1 million of page views, and we see how much memory does we use per element for the 1 million of page views, you see that it converges to 96 bytes, which is also really disappointing because it's like a lot of memory we're using for nothing. And if we get rid of the page view and let's just have a collection of primitives, the situation is mostly the same. So if you get a collection of integers, so for a list we use 40 bytes for integer. It's 4 bytes for integer itself and 36 for something. For a vector, it's a bit better, it's 20 bytes. For a set, it's much worse, it's 60 bytes, and it's also very disappointing. And it happens not just because the Scala collections were implemented in this way, because it's a trade-off of using a managed platform like JVM. And there is options, there are some escape from this. But before that, a short journey to how it happens on non-managed platforms, on C++. Does anyone comfortable writing C++ here? Oh, great. Me too. So we have just like a structure with a string and timestamp. It's not really correct to measure the size of the page view in this way because it will measure only the stack portion of the page view. But if you see how it's just located in memory, you just embed everything into a single structure. There is a length of your string, there is pointer to array of bytes, there is time right here, maybe some padding depending on the compiler settings. And if you put everything into a single vector, it will be like a continuous chunk of memory of all your objects packed tightly together without any, without much overhead. There are still some pointers to bytes, but there is no way to escape from them because bytes can be of different length. And this has pros and cons. The main con is that it's C++. The pros is memory usage, almost no memory overhead, and you have a lot of different knobs to tune for the compiler, for the code it generates, so you can just disregard all this alignment, pack everything as tight as possible, and it will work. For the CPU cache usage, it's almost perfect because your objects are in RAM in just a line. You don't need to go through the references, through the whole heap to fetch it. It's just straight, it can fit the cache. And the question is that can be achieved inside of the JVM without going to this native madness. And this guy wonders, and actually, yes, it can be achieved, but there are some problems. There are multiple options for that, and I'm afraid that it's not a complete list, but the main important things implemented. The first one is Project Valhalla. I guess someone heard about it. It's the project to allow Java Virtual Machine to use value classes. So in theory, it can embed your string internals right into your page view internals and like embed your page view right into the collection internals without any references and headers, in theory. But in practice, I guess it won't be on Java 10. So I don't know when we will see it in production. There is Chronicle Map and MapDB, which are really similar. They are like maps which are able to serialize something to bytes, but it requires a lot of boilerplate. You need to write serializers, deserializers, and if your case class is really rich and nested and so on, it will be really tricky to do it. For MapDB, it's also very map-centric. It's focused on persistence, and the problem is that it is broken with Scala completely. I don't know how did they get it. So it's some bug in the Kotlin compiler. It's written in Kotlin, and there is a bug in Kotlin compiler which is not fixed for the last 2 years, I guess. Maybe it's fixed already. I don't know, but you still cannot use it from Scala. It's just wrong byte code. How can it happen? The Scala of Heap project was very promising for me a couple of years ago, but accidentally died. And it has problems that you cannot use dynamic length object like strings there. If your case class has static size, like it's only integers, booleans, and so on, that's fine, it will work great. But for strings, not really. And there is Google Flat Buffers, which solves exactly the same problem, but the API is completely different. It's Google, and it requires a code generation step, and it's Java-centric. There are some wrappers for Scala, but it looks very foreign for Scala developers because it's just weird. And the situation is pretty disappointing for us and for me personally, that it looks like that you have no escape. And we decided just to sit and think, what can we do? What if we have something looking like Scala collections on a perfect world? It will be extension for Scala collections. It won't require boilerplate, so if you put a case class there, it will just work without need to write decoders and encoders for that, and it will have some acceptable overhead. So most probably it will be slower than Scala collections, but that's fine. That's fine if you're really ready to trade your throughput for memory usage. It can be acceptable for you. So and we just implemented something like this. Let me present a Scalapact. I'm not sure about the name because it looks not that interesting. So if there are any suggestions, but the Scalapact is practically an extension for Scala collections baked by the array of bytes. So, but like slides and words are words. Show me the code. So I will show you how it looks like. Here it is. No. So, okay, we have a page view, which can be like looking like this. I also implemented a function called measure, which just calls this gem tool to measure the memory usage of our case class. So it's 72 bytes according to gem. Let's have a list of this page views. This way, no. We'll just have some dummy page views with the name of string and the same for to long and to list to be completely sure. And we have just a list, and then we can see what's the memory usage of our list in a single call like this. Oh, it's 96 bytes per element, which is quite a lot. And but why can't we do this Scala collections madness with this? So it's packed list is the part of the Scalapact project. So and to be completely sure, well, let's just do some compaction on it, and it's 19 bytes per element, which is much better. Yeah. The cool thing is that there is not only a list, there is also a map, which can be done like in the same way. Map. It will be integer to page view to map. Integer to page view, and it should call itself map. Looks right. Okay, we have a map. Let's measure this map memory usage. It's 162 bytes per element, which is also quite a lot. And let's pack it in a way. We cannot use this to thingy because it's map. It's a limitation of Scala collections. It should be fixed in collection strawman, but not yet. To packed map, and it just seems the same, but how it's called? Pmap. Compact. So the compact representation. Measure. Measure. Oh no, the wrong one. Measure, and it is 31. It's much better than 160. And there is still a ton of this Scala collections method here. All of them are here because it's just a Scala collections extension. So here is my slides. So it looks like magic. But apparently it's not magic, because Scala allows you to do these tricks, and even most of the tricks can be done not only on the runtime but on a compile time. So for the serialization, how can we dump our case class to the byte array of bytes? It works like everyone does we have a type class for basic types like integers, strings, and so on. And if you have a case class, you just use Shapeless. Why not? Everyone uses Shapeless. Everyone likes it, using it, most probably. For example, we have our page view, and it has two arguments. We can transform it to the H-list representation, generic one, with just a string, long, and that's all. We already have type classes for string and long defined in the library, so you can traverse this list with these type classes and derive the one huge type class for your page view automatically at compile time. It looks and sounds great. What can go wrong with this? But there are actually different levels of complexity of that. So for simple cases like page view, it seems trivial. But there are other cases which are more complex. So we have like an easy one. The regular one, when you have trying to derive a type class for regular, but you don't have type class for easy yet. You can derive it manually, but it will be cool that you can derive everything at once for regular. The more complex thing when you have a recursive, when you have recursive type and like referencing each other, and the nightmare level with this ADT with the sealed traits, so you should have a way to serialize it somehow. But you can go down to the rabbit hole with the shapeless, but there are some helpers like label type class for that. So it looks really trivial, so you need to implement a type class for just end of your H list, the type class for the head and tail for your H list, and optionally you can do this for the coproducts for sealed traits, and it will just work. And it really looks much easier than doing all the things manually. So I still have, do I really have only 5 minutes? Just on the 20? Oh, I was surprised on that, okay. So, not 5 minutes, but like only 20 minutes past and it should be 40. Okay, okay, let's, and as an example of the type class derivation through shapeless, it's a regular way to play with it is the show type class trait show for the type t. It has a method print, which takes a value of t and returns a string. It looks acceptable. We also will define a couple of type classes for like long values and strings right here. Long show of the type, show long. And we can use this, so we can go this way and write new show long, all this override, blah, blah, blah. But on Scala 2.12, you can simplify it just to string. So pretty convenient. The same thing for strings. Show string and identity. Idea support suggests that it won't compile, but it will. It's shapeless. That's fine. And here comes the interesting part with the shapeless magic for that. Let's have an object magic. Extends label type product type class companion. The really long name, but I got used to it. We need the type class definition here, which is labeled product type class itself for the type class of show. And IntelliJ suggests us to implement a couple of methods for that. So the first one is the derivation for the h-nil, so for the end of our list, and it is just an empty string. Why not? The second thing is the derivation, which is really long, but just to break it into the parts. So we have an H list of head and tail. We have type classes for head and tail, and you need to construct a type class for the H list itself. So for that, let's have value and type class for head will print the head, and the type class for tail will print the tail. And it's still red. It's because we forgot for the third method, which is, I technically don't know why it's so required, but it's the projection. So how to generate a type class for F when you have a type class of G, and the projection from F to G, which is really straightforward when you get used to it. So it's value instance print to value. So that's all. And we should hit compile very accurately, you know. Things happen. Okay, looks like it compiles. It's already quite good. Let's import our magic into the current namespace. Let's also have a function which will derive our type class having the implicit for the type T, and we can also wrap it to the lazy so it will work with the recursive type definitions, and like show value. And technically that's all. So while page view show will be like derive show for page view, and let's hit compile, and bingo, it compiles, it type checks, and print page view show, print page view like hello, and the thing, and let's run it and see what will be dumped into the console. And we just iterated over the elements and serialized it into a string. The same thing works for, so it works in the same way inside of the Scalapact, but with the array of bytes. So let's continue. And if you would like to integrate your custom collection like we decided to do with the Scala collections, it's actually possible, but it's not really well documented because there are some blog posts, there are some Stack Overflow answers, but official documentation is not very transparent on that. But technically, you need to do two things to integrate with Scala collections. So you need to implement a builder thingy, which will construct your collection structure, mutably, by the way. And you need a type class for can build from, and with this thing you can plug it right inside of the Scala collections, and you can use this like two transformations and so on. Just transparently, you just need to have this implicit for can build from and scope. It will just work, and it is covered with pain if you are going to use it with the current collections, but it's still acceptable. For the lists implementation, it works quite in a straightforward way. So you just allocate an array of bytes, dump everything there, and if there is not enough space, you extend it, and that's all. And the cool thing that it will work even if you put primitives there. So it will, for like list of integers or packed list of integers on the wire on the RAM will be just an array of 4-byte integers without any object headers and stuff. There are still some problems working with this with the primitive values, but on the memory layout looks much better than before. So it's not randomly distributed among the whole heap. It's rather tightly packed into a continuous block of RAM. So for the page view, it has a size of the object itself, because it can have a different length depending on the string size. There is a length of the string field, the array of characters, the timestamp, and then so, and after that comes the next element, and the next, and so forth, so on and so forth. And I will just show you how it looks like. So, because I have a lot of time. In a list of integers, we will have a list. Oh no, not this way. We'll have a list of integers, and every integer and list takes about 40 bytes of memory instead of just 4. But we can do 2 packed map compact. I guess we will get rid of this compact stuff later, but it's still there. And packed list. Yes, you're right. And 4 bytes. Not exactly 4. There is some overhead, but it's okay. It's almost 4 bytes. which is much better than with just lists or vectors. For maps, under the hood, it is a bit more complex because you just, for the list, you need just to put the elements on the list and maybe traverse it from time to time. For the map, you need to get some elements from this list from the collection without traversing it. So we decided just to use the simplest possible way, just have an open addressing hash map. So you have a table with buckets. The buckets store offsets to the buffer. And in this buffer, there are just serialized keys and value pairs, right one after another. Our collections are immutable, so we don't really care about all the consequences of this decision yet. But it works like this. So if you need to put an element to this map, so for the open addressing hash map, you like compute the hash code of your key, get a remainder of the dividing it to the number of elements in the offset table. So let's imagine that our remainder is 1. So we have a free hole here, so we can put element here. We see that here starts the empty space on our map-backed buffer. We can just write the offset here on this position and just dump our object right here. When you need to get this object from this, it's a bit more tricky because it's open addressing hash map. There can be and there will be collisions, but you still like compute the hash code of the key, get the bucket, go to the offset, then check if the key matches the one that is stored on this offset. If it matches, that we got our element. If it doesn't match, you go to the next bucket, and so on and so forth until the world collapses. There are still some limitations of this collections implementation. The first thing is that they are immutable because if you are trying to implement an in-place update in a packed structure, it can be really tricky. For example, for the map, if you need to update an element laying in the bucket 4, so you need to write it somewhere here. If it fits, that's fine. If it takes less RAM, okay, that's fine. There will be some free space here. But if it's more than the space, you need like to mark it as an unused one, put it here, and then do garbage collection inside of we put garbage collection inside your garbage collection, so you can do garbage collection when you do garbage collection. So that's a problem. So we decided not just to mess with it. There are some data structures can give you something like this, but the implementation will be not that straightforward as open addressing hash map. So it's just a question of simplicity. The second thing is that the performance semantics of using this things are different. So if you use linked list, you know that prepending elements to linked list is almost free because it's linked list. Why not? When you have a packed list which is backed by array buffer and you need to prepend something there is no space on the beginning of the buffer because it's starting at the 0. So you need to either relocate or do some tricks writing your buffer not from the beginning of the buffer but from the middle of the buffer or something, which is also quite tricky. So, but it's still that. For map, it's mostly a problem of the definition, how the map is defined inside of the Scala collections. I don't have the definition itself, but like if you have a map of string to string and you have a map of int to string, and if you unite them, what you will get? The interesting question. You will get a map of any to string, which is hard to reason because you need to have an implicit encoder and decoder for the type of any, which is very interesting case. And you don't have one, and there is some ugly hack to do it inside of the collection. I won't show you it because it's a shame for me, but it works. And when you have a collection baked by the array of bytes, some of the methods of the Scala collections is 100 something. Some of them can be optimized considering the representation. So for example, when you get a size of a linked list, it actually traverses the list. When you get a size of a packed list, without the optimization, it will unpack the whole list while traversing it and get the count of elements, which is not very useful. But for our case, it doesn't unpack everything. It has a size prefix before each object. It just iterates over the sizes, and that's all. And computes the count without unpacking everything, but not all the methods are optimized. And if you decide to add something to the immutable collection, it will cause rebuild. Maybe we'll fix it somewhen. And still, if you decide to use it as a highly performant collection library for primitive values, you will be hit hard by boxing, because it's not a problem of the Scala-packed project. It's a problem of the way how Scala collections are implemented, because they are generic, not in a shapeless generic. I mean, that's a generic like a Java generic. So there is a type with type erasure, and you cannot put primitive value as a type for the generic object in Java. There will be always boxing. There are some works done in .t for that. There is specialization in Scala. In .t will be like auto specialization or something, maybe, who knows. But still, you will hit by boxing, and the performance won't be that perfect. There are some optimized collections for primitive values like debox and so on. Let's better use them. For the benchmarks, it's for memory usage of list of integers for different collection implementations. So you see that the packed list is quite well compared to other collections. For the map, for the list of page view, it's a bit worse, but still better than regular collections. But the interesting thing is, what about the CPU performance? How it behaves for the loss of throughput. So I just benchmarked a couple of things with this different collection implementations with GMH. So we have a filter benchmark, which is filtering your collection and building another collection with elements included according to the predicate. And for vector, it's like 11 microseconds. For list, it's 6 microseconds. For packed list, it's 14 microseconds. But it's not that bad, actually, because it's slower. It's almost 2 times slower than list. But some of the people like me are ready to trade off some of the throughput for memory usage. And if there is a way to cut your memory usage twice or 3 times, I'm ready to pay this. For this. For each, it does the same, but without the building collection. So the packed list implementations is almost 3 times slower. But it depends on your use case. Can you trade it for memory usage or cannot? It's up to you. For the maps, it looks mostly the same. So building a 1,000 element of packed map is almost twice as slow as just building a map, because actually it not only builds an open addressing hash map, it relies all the case values right inside of the buffer. That's why it's so slow, because map just uses the reference to the objects, doesn't deal with the object itself anyway. For the lookups, if there is an existing item, it's 2 and something times slower because of the object unpacking, because you need not just fetch the reference to the object, you need to somehow unpack it, and if the object is heavy, it can take a lot of time. It's for page view, as far as I remember, but it's still slower. The interesting thing that here comes the difference of the algorithmic implementation of maps in default map in Scala and packed map, because it's an open addressing hash map, and it can be a tree map or hash map, but it's not really a hash map. It's something more tricky, and that's why looking up non-existing element is much faster here, because you don't need to unpack anything. So some conclusions about the project itself. So at my company, so the question is, are you using it in production? And to be honest, no, because because we're not sure about the quality, because it's like an early development. It was just a test of the idea. Is it possible to do it? So most probably we will continue developing it, but there are still some bugs. So I just was optimistic and tried to replace one of the collections I would like to pack in our production. Well, not in production, of course, but this was a real application code, and it crashed in some super weird way. It's just, I still don't know what happened. But on the just simple tests, it works quite well. It was my first deep encounter with Shapeless, and I surprisingly liked it. So I really recommend. There's a Type Astronaut Guide to Shapeless book, which is an interesting read. It can see very, like, it starts like, oh, see, there's a H list, and then on the second chapter starts like, aux generics and some weird things happening. But you might need this book at least maybe 2 times or 3 times to get all the things there. But it's still very interesting. For the project itself, it's available on GitHub. It's published on Maven Central, so you can just play with it without any issues. For Java object layout, it's a part of OpenJDK. So just take it. There is a SBT-Joe plugin, which is also published, and it's by Konrad Malawski, as far as I remember. And the Jam is also on GitHub on Maven Central. You can use it. It's very trivial to use. There is a lot of docs, but it's still one function call to get the memory usage. And that's all. You can ask questions for me. Yeah.
What happens if you try to serialize these packed lists of a cryo or a plain Java serialization?
Yes, we considered using this, but if you go to this route, you won't really have control of the way how it is serialized, and you can have some tricks to work with the serialized data itself while in collection, like counting elements in a list. You don't know how many elements there. If you use Creo, you might need to unpack one by one and get the final count. But for us, we have like a small header with the size of the object. You can just iterate through the sizes and get the number of elements there. Or you can, in theory, do some sort of lazy unpacking of elements. It can be used.
My question was not...
Sorry? For Creo, there are different ways of serializing. So there is a way to hard code your class names like an integers, and that's all. But yes, but in this case, it's all done on the compile time. So your type class for serializing the page view knows that it's a page view. You don't need to, so it's your choice how to deal with bytes. But yes, you can serialize it as a page view and try to get the array of bytes from there, and then deserialize it as I don't know, like not a page view, as a click, and it will most probably crash.
My question was not about comparing that to what Cryo does to the individual objects. Was to take the complete packed list of 1 million page views and use it through Cryo or through any of these serializations that are used in Spark or whatever. To minimize the amount of crap that gets serialized around the steps. Can you try that?
For serializing everything through the Cryo, no, I don't try it, but I don't think that it will have a dramatic difference. So when you serialize through Cryo, you can do some compression, for example, with LZ4, and it will take even less memory than the packed list, but it's not like the scope of the solution to not only pack, but also compress. Maybe in the future, but it's already slow. If we get a compression there, it will be even more slower. So, yeah, so.
To create a packed list, you first have to create a regular list?
No. So I will repeat the question. So to create a packed list, you don't need a list. So you can, there is a constructor like just putting the variable list of arguments for like packed list with the brackets, and it will just construct. You can transform your list to the packed list or any way. It's just a part of Scala collections. How you can build it in the same way you build just list.
Follow up. So for the case class to serialize it, it will be converted to a edge list.
Yes, but only on compile time. No. So I will try to repeat the question as I understand it. So does the H-lists exist on runtime and should be garbage collected after all? So shapeless, and well, you have a H-list. It's not really a list as you get used to it in the Scala collections. It's like a recursive type, and it traverses it on a compile time with implicits. So we didn't see any overhead. I've never ever seen that there will be some H-lists on runtime because they should be gone after the compilation. So when you derive a decoder for the page view, for example, it is just a class which will write the size, then it will write the string, then it will write the long value, and that's all. There won't be any H-list there. It's just the type class will be generated on compile time.
Yeah, the type class will, but there is a representation of your strings and integers in the form of a H-list. There's an H-list type corresponding to the case class generated at compile time. It is a generic, that
Yeah.
label generic that
Yeah.
converts your case class and its content into H-list.
Yeah, it can be. No, but so.
So it's not a problem.
Yes, but that is also not a question as far as I got.
Well, I'm just curious, is memory pressure?
So we've never measured this thing. Oh, sorry, it blocked, but no one cares. So we've never measured, so technically I don't know. So?
Insoles 200, I would say. Yeah, no. So what's wrong with the set? On one of your slides, you had a set, chart with sets that was doing completely different lengths in comparison to the rest of the...
Oh yeah, I can explain it. Maybe it's here. No? Like this. So you see this so at the top. It's just in a way that set is implemented, so it has some free space inside to accumulate your elements, so it preallocates something, and you see that the scale is, the scale is logarithmic here, so it's not just happening every some fixed period. The period is also logarithmic, so it's like every twice, so it just doubles the backing collection for the set every couple of elements. That's why. And it's not done for a list because it's just a linked list. It's not done for vector because it's a very complex structure. It's not.
Once again, what happens in the beginning?
At the beginning, it's just this crazy thing happening at the beginning is just the initial buffer. So you can tune it for a packed list. It allocates, I don't know, 100 bytes or something at the beginning, but you can allocate 0, and it will be always tightly packed. That's the problem of the initial buffer, because we count the how much RAM used per element. That's why if you have only one element and 100 bytes buffer, it will be a lot. Okay.
How do you think it should be used? Is it a list for lists that would use a bunch of memory that you will query in a sort of in a way, and then use the extracted data to perform some business operations, or should it be used directly to perform some business operations?
It's up to you. So for our case, so we have a couple of thousands of merchants, and we have product lists. They are updated really not that frequently. They are updated, but that's fine to recreate this collection once in an hour or 2 hours. And they are technically fixed, and these lists of products can be really huge, so there can be a couple of millions of products there. And that was a really problem for us. If you get a very rich case class describing the product on a merchant, and you have 1 million of these case classes, and they are inside of a map, and it can consume 8 gigabytes of RAM, and it is quite a lot, and it causes some garbage collector issues because there's a lot of objects, a lot of references happening there. So when you plug this packed map there, because it's baked only by a single object, it's just an array of bytes, it doesn't hit you with a garbage collector because it's just a single object, not a million. And the memory usage itself is much better. So that was our initial use case, but we're not still there. We're just moving in this direction. So, if that's no questions, that's fine. Thank you.